on to the next question. Question 4. Okay, so it's saying we're looking at a posthumous study, see if the effects of the number of years a person runs to see if the number of years a person runs affects how long they live. Okay? And we collect the life lengths of 20 people and found how long they ran before dying. Okay? And now we're given a few things. We're given X bar, Y bar, R, SY, and SX. It's a lot of things, but you need this. It's a big data set, so I would find it cruel to make you do this. So I did it myself. SY is 9.5, SX is 10.5. R is 0.912. Okay. And we want to fit a simple linear regression. Okay? Simple linear regression. And we actually can do that given all of this information. Now, if you wanted to find either of these, you would have to do, and I'm not sure if you're going to have to do this, but okay, so what this is saying is, this is a scary notation, understand that. What this is saying is that you take each y value, subtract the mean, and square it for each y value. So there'd be 20 in this case, and there would be whatever the amount of n in all the other cases. So Sx and Xy are computed in the same way, but if it were Sx, you do x minus x bar in this case. And you add them, you take x. So in this case, for the x values, it would be 5 minus 11.75 squared plus 8 minus 11.75 squared, all the way to 8 minus 11.5 squared, which is the last observation as well. Okay, and if you want to find SY, you do 65 minus 75.5 squared plus 70 minus 75.5 squared 20 times. But I did that for you because I'm not going to have you subtract 20 things and square them and add them all up. Okay, so we want to find our regression equation. Now remember, this regression equation is trying to predict this regression equation. Okay? This is the true unknown regression equation. Okay? We're trying to predict it. And the way we predict it is by finding A and B, and they're actually the best A and B that you can find with the given data. Okay, so to find A and B, you do y bar minus b x bar and r sy over sx. All right, so we have all this stuff. Let's find b first, as we have to. So it equals 0.912 times 70, nope, 9.5 over 10.557. And that equals, after some small calculations, 0.6646. 0.6646. And then plugging that in, we got 75.5. Oops. Let's erase that. 75.5 minus 0.6646 times 10. Times 11.75. Okay? And that equals 6907. 6907. Yeah, you guys should check this at home, because I might be wrong, but I'm not. I just have to check this. Okay, so, but you should check for yourselves. So, okay, so we're going to just fill in A and B. So y hat equals 69.67, sorry, 7.6907 plus 0.6646xi. Okay, so what this means is that if you plug in the amount of years a person ran, it'll give you a predicted value. It'll give you a predicted value for how long they lived. Okay, so we have our equation. We'll write it up here to save space. Y hat equals 67. Okay, this is our regression equation. This is really what we want. Okay, so it tells you to find the regression equation. Okay, and now what we're going to do is to run basically an Anova test to see if it's likely whether or not this slope is 0. Okay, so not all of you that are watching this may have done this before, and you might not be in your class, you might not have done this, but you'll do it eventually, I promise. Okay, so we're going to run an Anova on this regression equation, and what that is doing is telling us which line is better. This is y bar, and this is our regression equation. So we have our data points, and this is our regression line, okay? And what the Anova is doing is telling us which line better predicts these data points, or better predicts the data points that we're given, okay? Excuse me. Okay? And the way we do that is by testing, by making a ratio of the amount of variation. What this is y. Sorry. Nope, this is SSG, or SSR. This is okay, so as we were explaining before, we were explaining SSE, SSR. Okay, so we had before that this was the equals 1 to n of y minus y bar. Nope. Okay, as I was explaining before, SSE is that other component of doing the test to see whether or not beta equals 0. I minus y hat. Okay, so this goes back to kind of creating components of the ratio of seeing whether or not we have our data points, we have our line, we have y bar, and okay, so we have our data points, and we have the residuals, that's yi minus y hat. We have the residuals, and then we have, for each x observation, we have the differences, the squared differences, the squared distances between the expected value and the mean, okay? So what we really want to know is whether or not these are significantly different, okay? Whether or not there's a chance that the true line could just be y bar. Because if you notice that if you're doing, you're finding your a, and when you're creating your regression equation, it's a equals y bar minus b x bar, right? And if b is 0, a just equals y bar, so your y hat equals y bar. Okay, that's why you're wondering whether or not. They're the equivalent statements. Okay, so you want to know, basically, if all of the difference between this line and this line is basically because there's a huge amount of difference between the observed and the expected values, or if a lot of the difference is because there's actually a lot of difference between the mean and the expected y values. Okay. However, in this particular problem, and not in most problems by any means, most problems you're going to have to find these values. Okay. However, it's a pretty big data set, so I decided just to give you SSR and SSTO. Okay. Now I haven't explained SSTO. SSTO is, of course, the indice goes from that to that, and what this is saying is that it's the total variation of the whole regression equation. So it's yi minus y bar. Okay. Okay, and there's a relation that says SSTO equals SSR plus SSE. Okay, you may not, or you may know that. Okay, if you have two of them, you have all of them. Okay, so in this particular instance, we have SSTO equals 1715. And we have SSR to be 935.45 plus SSE. So if we solve for SSE, we find that the SSE value is 779.55. SSE 779.55. Okay, so now we're going to create our Anova table, okay? So I'm sure all of you who are watching this video hopefully go to class and have seen this. Can't be sure, but hopefully. And if you don't go to class, you should. SS. Okay. So the source of the error and the source of the regression. Okay, so you have regression. And you have error. Okay, now the degrees of freedom associated with regression are always p minus 1. Okay, what's p? And this is n minus p. Okay, what's p? P is the number of predictors. So remember, the true equation is mu equals alpha plus beta x. Okay? But our predicted equation is a plus bx. Okay? No, so with this equation we're predicting two values, alpha and beta. So in simple linear regression, the number of predictors minus 1 is 2 minus 1, which is 1. Okay? And n minus p in this particular instance, so it's this number, the number of observations, which is 20, minus the number of predictors, which is 2, is 18. Total is n minus 1, which in this particular instance is 19. You'll notice another equality. This is always true. dfr plus df E equals df total. Okay? Okay, so we have two of these. We have 1 and 18, so we know this one's 19. Okay? And we have SS whatever. We have 779.55. We have 1715. And our SSG was 935.45. Okay, now to find these mean square errors, which is the ratio we're going to create, so we have to basically divide by the number of degrees of freedom. Like, if you think of the regression as it's one equation, you're observing one thing. That's why it's 1 degree of freedom, and you have 18 possible degrees of error. So you divide SSE by 18. That's kind of like a heuristic, a literal kind of description of it. It's not exact, and I don't know why. You guys don't need to know why. They haven't told me yet. So just for now, take my word for it. So you divide each of these by their degrees of freedom. So 935.45 over 1 obviously equals just 935. And 779.55 divided by 18. And that equals, and this equals 43.31. Okay. 43.31. Okay. So you guys should check all these at home. I think it'll be extremely useful. Okay, and now to find our f value, we just divide the two. Okay? Let's see. The f value is 21.6. 21.6. Okay. Now this is our f star value. What does that mean? Okay. I'm gonna erase all this stuff. Okay. What the f star value is our observed f value. Okay. Now, if you look on the f table, looks like this. It has f table. Okay. And if you guys don't know this, that's all right. So this is df1, this is df2, okay? And this is always 0.05 alpha, okay? At least in this class. Okay? So if you look at df1 and df2, which are your numerator and denominator of your f statistic, that's what you're going to look at. So we look at f1 and 18, so we go, so it goes 1, 2, infinity, 1, 2, 18, infinity. So we go right here, and this value happens to be, and you guys should check this just to make sure, the f value of 1 and 18 is 4.41. Okay, so now to find your p-value, well, not really find your p-value, to decide whether or not you reject or accept h naught. So this is f table. This is 4.41. Okay? We found, however, though, that an f value of 21.6. Okay, so this, remember, okay, so this whole area is 0.05. Okay? This is our f calc. This is 21.5. Okay? And the area that's associated with 21.5 is just this area, okay? Now, if this area is 0.05, this area is smaller than 0.05, okay? And the area is the p-value, okay? So this can be interpreted as the minimum f value needed to reject h naught, okay? So this would give us a smaller than 0.05 p level, probably around 0, actually, which would mean that the probability of getting the regression line that we received from the data, if the true regression line were just the mean of the y's, there would be a 0% chance of getting the regression equation that we found. So obviously, the true slope of the line is not 0, and that's the answer to the question. Yes, that is your conclusion. Okay, and so if you get a big f value, that means you get a small p value, okay? And if you get a small p value, you reject h naught. Simple as that. All right, that's the end of question 4.
The Teaching Center. UF's Learning Resource Center.